We already met this application. It's literally where he was born. But let's actually quantify it. Say you invest 100,000 rupees at 8% annual interest for 10 years. Compounded annually, you end up with about 215,892 rupees. Compounded monthly, 220,996. And compounded continuously, using E, 222,554. Notice the gap between monthly and continuous is small, only about 1,558 rupees. Continuous compounding sounds dramatic, but really, it's just the mathematical ceiling that more frequent compounding is already creeping toward. Bernoulli's original insight, now with real rupees attached. Everything in this next section is the same idea wearing different costumes. Any quantity whose rate of change is proportional to how much of it currently exists follows this equation. dy dt equals k times y. Solve it, and you always land on the same shape. Y of t equals y naught times e to the kt, positive k, growth, negative k, decay. Unconstrained population growth. N of t equals n naught, e to the rt, where r is birth rate minus death rate. Of course, real populations don't grow forever. They hit resource limits, which gives the S-shaped logistic curve instead. But that curve is still built from E underneath. Radioactive decay. N of t equals n naught, e to the negative lambda t. Ask when the quantity drops to half its starting value, and solving that equation gives you the half-life formula. T1/2 equals the natural log of 2, divided by lambda. Newton's law of cooling. The rate a hot object cools is proportional to the gap between its temperature and the surrounding room temperature. Solve it, and you get temperature of T equals room temperature plus the starting gap times e to the negative kt. Worked example. A cup of coffee at 90 degrees Celsius in a 22-degree room with a cooling constant of 0.05 per minute. After 20 minutes, the coffee has cooled to about 47 degrees. Same shape again, this time in pharmacology. Drug concentration in the bloodstream decays as C0, e to the negative kt, and the elimination half-life uses the exact same formula as radioactive decay. That's not a coincidence or a metaphor. It's the literal same mathematics. And in the early stage of an epidemic, before enough people have been infected to slow things down, the number of active cases grows the same way. I of t approximately equals I naught, e to the rt. This is exactly why epidemiologists plot early case counts on a logarithmic scale. Exponential growth turns into a straight line, and the slope of that line directly tells you the growth rate. Now for something less obvious. Why does he show up in the bell curve? Start with a binomial distribution. Say, flipping a coin many times and counting heads. As the number of flips grows large, the shape of that distribution starts to look like a smooth bell. Using an approximation for factorials and zooming into a Taylor expansion around the peak, that smooth shape turns out to be exactly e raised to the power of a negative quadratic, the Gaussian formula. E also governs a specific kind of spiral, the logarithmic or equiangular spiral, described by our equals a, e to the b theta. You'll find this shape, or something close to it, in nautilus shells, hurricane cloud bands, and spiral galaxies. Here's what makes it special. The angle between the spiral and any line drawn straight out from its center is exactly the same, everywhere along the curve. Here's why. Zoom into a tiny piece of the curve, not to scale. Moving along, it is really two tiny steps happening at once. Outward, away from the center, a distance we call dr, and sideways, along the circle, a distance r times d theta, since that's just ordinary arc length. Those two steps are perpendicular, forming a tiny right triangle, and the curve itself is essentially its hypotenuse. So the angle between the curve and the radius, psi, has a tangent equal to opposite over adjacent. Our d theta over dr. That's tan of psi equals r, divided by the rate of change of r, which works out to a constant, 1 over b, no matter where on the spiral you measure. That's why the spiral is self-similar. Zoom in or out anywhere on it, and it looks identical, just rotated. Here's a lovely, slightly tragic real-world instance. Moths evolved to navigate at night by keeping a constant angle to the moon, a light source so distant that its rays are effectively parallel. So constant angle just means flying in a straight line. But when the nearby light is a candle or a flame instead of the distant moon, keeping that same constant angle no longer produces a straight path. It produces a spiral, inward, toward the flame. One honest caveat, since popular science often overstates this. Real nautilus shells only approximately follow a logarithmic spiral, and their growth rate parameter is not fixed to the golden ratio, despite that claim circulating widely. Hurricanes and galaxies follow this shape for genuine physical reasons involving angular momentum, but the fit is approximate in both cases, not exact. In data science, E shows up constantly. Start with logistic regression, a tool you already use. If P is a probability, define its log odds as the natural log of P over 1 minus P. Solve that equation for P, and you get the sigmoid function, 1 over 1 plus e to the negative x. This S-shaped curve is the backbone of logistic regression and the activation function inside countless neural networks. Extend the sigmoid to more than 2 categories, and you get softmax, e to the power of each raw score, divided by the sum of e to the power of every score. It converts any list of numbers into a clean probability distribution that sums to exactly 1. This sits at the output layer of nearly every image classifier and language model. Last one, a genuinely surprising appearance. Imagine throwing n balls randomly into n bins, 1 ball at a time. This is exactly how hash tables and distributed systems distribute data. As n grows large, the fraction of bins that end up completely empty approaches 1 over e, about 36.8%. Same number, showing up again, this time inside the machinery of computer science. Step back and look at everything we've just covered. A navigation table, a bank account, the area under a curve, an infinite series, population growth, radioactive decay, a cooling cup of coffee, an epidemic curve, the bell curve, a nautilus shell, a moth's fatal flight path, and the neural network reading these very words as I say them. Every single one of these is the same underlying number, appearing again and again, in problems that have nothing to do with each other on the surface.